All right, what I want to do today is first I want. Oh, my God. I pick that up right there. What I want to do is answer a question that somebody asked, and I think it'll help everybody. And then I'll take a couple other questions. So let's see if this works. So the problem we did last time, we had three symmetric, concentric, spherical surfaces of charge, right? I want to just go through this briefly with you, and I'm going to show you how you think about it and do it. Y'all with me, class? So we're going to have, and I'm just going to arbitrarily show this. It doesn't matter whether I'm going to have an outer one at radius, call it C, and it has a charge density rho C. That's a charge density in coulombs per meter cubed. Then I'm going to have a charge density here at a radius B, and the charge density is simply going to be rho B. Y'all, that would be in coulombs per meter cubed. Doesn't matter what they are, really. The values, it doesn't matter what C and B is, as long as C is greater than B. Finally, I'm going to have one here. It's going to be a radius A, and I'll have rho A. So we've got three concentric charge distributions. Y'all with me? Now after that, I'm going to just do this. I'm going to say the total charge on surface C is just the charge density, rho C, and it's times the surface area, which is 4 pi A squared, or C squared. Does everybody follow me? The surface area is 4 pi R squared for a sphere. If you're at radius C, that would be the surface area. Surface area times charge density would be total charge. How many got that? All right, now we'll do the same for QB, which is just rho B times 4 pi B squared, and QA, which is rho A times 4 pi A squared. Now we have three different total charges associated with the spherical shell. With me? Now, if we assume that the voltage as R goes to infinity or equals infinity is 0, that's the assumption of the statement, then we can say if we are outside of C, there's going to be conditions. So the first one is for R greater than or equal to C. The voltage can be found, and I'm not going to go through the method to do this, but you can calculate the total D field outside of the region, R equals C, by taking all that charge, putting it at the origin, A, B, and C, dividing by 4 pi R squared would be the D field. If you divide that by the E field, or by epsilon naught, you get the E field. And if you integrate the E field from infinity as the 0 point to any point in there, you're going to get a 1 over R 4 pi epsilon naught with the total charge. Do y'all follow? Give me a show of hands if you do. No? So, how many? I mean, really, it's just taking it all and making it look like a point charge at the origin. That's all it is. So the total charge is QA, QB, and QC. You don't follow me on this, class? Just put it at the origin. That means if I look at the voltage here, V of R is just the total charge, QA plus QB plus QC, and then you divide it by 4 pi epsilon naught R. Now that's true as long as this condition is so. With me? I'm going to show hands if you see that. Now we're going to go between B and C. So the second condition is when R is greater than B, less than C. Don't worry about greater than equal to right now. Now, what you end up doing is, if you would integrate the E field, right? The E field is actually going to be pointing this way. This is the E field. If you integrate the E field from all the way out there to infinity to this point, remember it's minus the integral, of E dot dl from the outer point, which would be infinity, to the inner point, which would be C. Do y'all follow me? You're going to get a voltage that has to do with this very value when R is replaced by C. Y'all follow me? Give me a show of hands. So now you're going to get the voltage at this point, but then you still have an electric field here, in here. Y'all with me? Give me a show of hands. It's between this one and this one. That field can be found from Gauss's law. If you take this charge and this charge, QB and QA, put them all at the origin, right? Then do the integral of d dot ds is equal to the total charge enclosed. Well, the surface area is 4 pi r squared, right? You divide it by QB and QA is the total, or QA plus QB is the total charge. Divide that by 4 pi r squared, you would have the D field. Let me see your hands if you understand. If you divide that by epsilon naught, you get the E field. Now, if you integrate minus that from the outer one to any point R in between there, you're going to get the additional voltage. Do y'all with me? I'll put it up here. So for this one, V, this is the condition now. V of R, assuming infinity is 0, is going to be the voltage at R equals C. Y'all with me? That's that. Plus would be the minus the integral from C, and it's going to be to R of, now this would only be QA plus QB over 4 pi epsilon naught, and it's going to be R squared dr. Everybody following on that? I'm putting a formal way of doing it, right? What are you really doing? You're going to be adding the voltage, right? This voltage that would be found by adding the E field integration from here to here to the voltage already at the value of C. Y'all with me? Give me a show of hands if you see this. And just for completeness, because I have a few things I want to cover. Not really. How many understand this, right? It's going to be higher here than it is here. Y'all with me? Everybody? All right, now what about at this point, what is it? It's just the voltage here plus the voltage that would occur here. Right? I mean, really, you could do the integral of the E field from here to here and then evaluate that value of voltage. Y'all with me, class? Let me see your hand. All right, then you would add, now if you're inside here, what's the added voltage? Just tell me, and why? Why is it 0? You're right. Why? There's no E field, right? Think about the integral of d dot ds. If I'm from A to B, there is an E field, right? But inside of A, y'all follow me on this? Because inside of A, if I do the integral of d dot ds equal to the charge enclosed, it's charge enclosed is 0. There is no electric field. Give me a show of hands if you see that. So the voltage at A will be constant from A to 0. Got that? One last time. You all see this? Did I answer your question okay? And you understand this. All right, now I'll warn you about one thing. And I try to caution people about this. If these are all positive charges and infinity 0, the closer you get to that charge, the higher the voltages. Y'all with me? The closer you get. You hit this point, it'll have a value. Keep going in, it's going up. Hit this point, it's got a value. Keep going in, it's going up. When it hits A, that's as high as it gets. Y'all with me? And if I ever gave you a voltage and I wanted an E field, you would take minus the gradient of the voltage to get the E field. Y'all follow me on this? Now show of hands if you do. This is really very similar to Gauss's law. The differential form of Gauss's law is div of D equals rho V. The integral form of Gauss's law is the integral of d dot ds is the charge enclosed by that surrounding region, closed region. If you think about this, the integral of E dot dl, now it's a dl and it goes from A to B with a minus sign, is really equal to the voltage difference, is akin to the E field is minus the gradient of the voltage. It's the same type. That's a differential form and there's an integral form. How many understand that? Try to appreciate the similarities in all these things, or at least why one is an integral and the other is a differential form. Now I want to cover that. Now, next thing I want to cover, I gave you a bunch of problems that I hate. And I gave you solutions, or at first, the bunch of problems I first put up, they were out of the 6th edition. I had the 5th edition solutions. They didn't match. So then I put up a bunch of problems. I think it was the 7th edition, and the solutions, all of them. And those problems are the same as the first ones I put up, but their numbering scheme's a little different, I think. Y'all with me on this class? They're more difficult than Wentworth's problems. That's the book I have. It'll challenge you. But if you get that down, you do those problems, you'll understand it. If you work through them and make sure you see this stuff. I'll take one last question before I move on with myself. Anybody got one? Because that stuff's pretty clear if you read it and just look through the problems and do them. Anybody? All right, I want to cover one topic today. And in your book, what time is our game? Is it 2:30 game this week? I'm just trying. Okay, never mind. I'm asking that. Had nothing to do with the class, but I'm just thinking about parking. Oh, I won't be able to park downtown. So we did the electric potential. The next thing in the book is going to be conductors and really resistance. Y'all with me, class? I want to go through this with you. You've had this before, and I'm trying to make sure I make it as simple as possible to understand without making it too simple. And you're going to see that this is going to be sort of the same approach we use to calculate capacitance. And you've actually had all this one other time in physics, at least you were supposed to. Physics, they don't tend to do problems that are more complex, but they get the basics apart. A good physics professor will do a good job with that. So this is section 310, and I want you to understand something. It's not hard if you follow, but it can be very confusing if you don't keep up with this. So if we talk about conductors or really resistors, really I want to talk about resistors. So you're used to resistors looking like cylinder, very small cylinder, like quarter-watt resistors with a color code, right? And they have a resistance value and a tolerance on it. But here's how you actually calculate resistance of anything. And I want to take you through the steps. Let's say we have something, and I'll make it a cylinder because that's what you're used to seeing for resistors. And the length of this is L. And now we're going to say the cylinder has a radius of R, call it RW. And it has a conductivity sigma. Doesn't matter what they are. I'm going to make one assumption. There's going to be a cross-sectional area here. The area of that is simply pi RW squared. Do you all agree with that? That would be in meters squared. Y'all with me? I'm going to assume that cross-section doesn't vary down the length of this. Now, it doesn't matter if it's a cylinder or if it's elliptical or if it's rectangular or anything like that. What matters is the cross-section doesn't change versus the length. So then I start, but I'm going to assume that I have a battery here. And the battery has some voltage that we don't know. I'll just call it V0. And assume the surfaces here and on the back are metallized. Now the reason I'm going to say I'm doing that is that way the potential difference from this planar surface to this planar surface will be the same. Y'all with me? The metal just means there's no voltage drop. Everybody following on that? Now I'm going to assume I have a current coming in here, a current I0. Now follow the steps on this. The way you do resistance problems, almost always, the first thing you do is assume I. Then after you assume I, you don't know what it is, don't put a value. The next thing we get is J, the current density. Now, you might as well give this a direction. I'll call this the z-axis, but it really is inconsequential at the end of the day. Can everybody see this in the far back, guys? Right back there? All right. Now I want to get J. What are the units of, that's current density. Do you remember the units of current density? Think about it. Density. Current's units are amps, right? Density would be per meter squared. Follow me? Everybody with me on that? So here it would be I over the cross-sectional area in the AZ direction. Now the units of this are amps per meter squared. So it's I over pi R squared, RW squared. The units would be amps per meter squared. So I got J. After I get J, I get E. This is a straightforward one. It's the easiest problem for resistance. E, do you remember that J is equal to sigma E? How many remember that? Anybody? You guys don't remember? You remember? Good. Nobody else? That's very important. You're going to need to know these relationships like the back of your hand. As a matter of fact, you're going to have to know for your senior level courses in EMAG too. If you don't, you really kind of just fall off the page. So E would be J over sigma. Do you agree with this, class? All right, so if I do this, what do I get? I get this equal to I over sigma, and then pi RW squared. E field is in volts per meter, and it would be in the AZ direction. Do you all follow me on this? Now the next step is we want to calculate the voltage. That's this voltage, but in terms of the current. So we integrate the E field from here to here. The E field would go from the positive, right? This would be the direction of the E field. Does everybody follow me on that? So we want the voltage difference. And don't worry about the sign. It's always positive. All right? It's always going to be a positive value because we're going to divide that by current to get the resistance. So the voltage between those, and you could put B to A if you want. It won't matter. It's really going to be minus the integral. It could be from A to B of that E field, which is a constant, and that's the E field dot DL. Now, if you look at this for a second, DL is going to be DZAZ. Do you all agree with this, class? Right? How many see that? Now we can put it all in there, but the E field's a constant. So I can say that's really just the integral of E, which is I over sigma pi RW squared in the AZ direction dot AZ DZ here, and you can go from 0 to L. And you're going to get I over sigma pi A or RW squared, and then it's going to be times L. And that would be the voltage difference between here and here. You all with me? Give me a show of hands if you see it. It's not hard to see. Finally, the resistance, and these are the steps. Start there. The next is the voltage. The final step is the resistance itself between the ends of that cylinder, are simply the voltage divided by the current. That's the voltage divided by the current. It's L over sigma pi RW squared. And the units would be ohms. How many see that right there? Follow me? Now that's the procedure used to calculate the resistance of any kind of any shaped resistor. I'm going to take you through one more. You all with me? Yes, sir.
Where's the I in the, is there supposed to be
Where?
and
Here?
yeah.
It divides out. Voltage by current is resistance. That's the reason we assume the current, and then we find what voltage it creates, and we divide the voltage it creates by the current. Assume current, and you get the resistance. Do you remember seeing this in physics class? How many do? You do, you do. This is a classic physics problem. All right, it's the simplest resistance. Now I'm going to take you through the next type of resistance calculation. I'm going to go right to spherical. Cylindrical, you can either go down a length or you can go from the inner to the outer conductor. They're really not that tricky. So let's assume we do spherical. This one takes, I've got to make a comment about this. So I've got an outer surface here and an inner surface. Let's call the outer surface has a radius B and inner surface a radius A. And between A and B, assume these things are metallized, I have a conductivity sigma. Again, this is a classic problem. Y'all with me? Now, assume you bore a little hole right through here. I'm trying to give you the whole visual effect. And you put a conductor there. And then you come down here and take a battery. And this is going to be a battery with some potential V naught. It's also going to give rise to a current I naught. And assume this outer sheet is metallized. Now assume the entire inner sphere is metallized and the outer sphere is metallized. Do y'all follow me in this class? Show of hands if you do. It's a ball. You got a thin little hole in there. It's so you can take this wire, not touch the actual conductor here, go straight through, touches there. So we do this the same way. We assume I. Okay, we're assuming a current I. With me? You can call it I, doesn't matter. I's fine. Matter of fact, I'll call this assume I naught. After that, we're going to get the current density. Now, here's where the assumption is made. Current's flowing in here, it hits this metallized surface, and the same amount of current density will flow in at every angular position for any theta and phi. So the density of that current will just be equal to the total current I over a surface area that would have to do with the radius R here. You all with me, class? Remember, we're in spherical coordinates. How many see this right here? So to get this, we take I and we divide it by the surface area of a sphere, which is 4 pi r squared, and it's in the AR direction. Again, units of current density are amps per meter squared. With me? Good with this, everyone? The next step is what? Can anybody tell me? I got J. What do I need next? E, right? I need the electric field, correct, class? Because I'm going to do the integral of E dot dl from the inner to the outer conductor to get the voltage. So what's the E field? It is simply what? J divided by what? Sigma. Isn't it, class? I put that up. Y'all with me? Let me see this. Say again?
We're good.
Y'all see this, class? This is a straight, it's the method you use 99% of the time. There's one exception, I'll get to that. Now, after that, I have I over 4 pi r squared divided by sigma, and that's E, call it in the AR direction, right? Finally, I'm going to get the voltage between the inner and outer conductor. With me? That's this voltage. And I'm going to say V naught itself, technically it's equal to minus the integral from A to B of that field, which is I over 4 pi, and then it would be sigma r squared AR dot dl. Now we could write the full dl, but the only component we care about is dr. So it's times dr AR. When you go ahead and do that integration, what do you get? You get I over 4 pi sigma, right? And then this integral, the integral of 1 over r squared is minus 1 over r, right? Then you end up getting what? 1 over the actual inner radius minus 1 over b, right? And when you do this, that is the you can call that the voltage difference between the inner and outer conductor. Now, the resistance is always a positive value for anything that is a linear material. The only time you can get a negative, it's not really, but a quote negative sensed resistance or differential resistance is if you have an active material or like a semiconductor that's actually got a potential on it. All right, so I'm not going to go there. So that means the actual resistance between the inner and outer conductor, and it doesn't matter if this is plus, this minus, or this is plus and this minus, because resistance doesn't care about the potential difference. So that's equal to simply V over I, or it's 1 over 4 pi sigma, and then it's 1 over A minus 1 over B. And that's the resistance in a nutshell that you get between the inner and outer conductor for this system. How many see this? Okay. Now, if for cylinder, it's the same method. I'm going to give you a couple problems on that. Next time, on Friday, I'm going to go through this and capacitance. All right, please be there for that lecture. It's an important one. And do the problems. I'll give you a quiz now. Let me go and get this off.